Yeah, good evening. We'll just start in a few minutes. Yeah, Okay. Good evening, everyone. So I'm just waiting so others can join. Very few people are there, so that's why I just waited. So this was the second session on the same course, that is Principle of Casting and Technology by Professor Pikeja. I'm one of the tutor for this, like TA for this. So my name is Rakesh. I'm a doctoral student at IIT Bombay. My main research involves light metal processing and characterization. Okay. So I think the screen is visible and my voice is clear. Uh, we can proceed with the session today. Let me know if there is any difficulty in listening or whatever.
Yes. So my okay, thanks. So let me start with a brief, overview of this last week session. So this entire session will be on week one lessons, some of the calculations, some of the problems, and some of the fundamentals regarding this casting will be discussed in this lesson. Then followed by some of the numericals at the end, which will be helpful for your assignments. So as you can see. You are I think everyone is aware of this casting technology, I hope. So generally this is a very simple process which was a very old process, you can say. This was the starting process of this manufacturing, and still today it was used, even though there are new technologies evolving. This casting, the if you see, there are so many things involving in this casting. One is the process, that is simply heating the metal and pouring it into the required molds. And there are one more thing involved, that is a mechanism, which is the solidification mechanism, which can be applied anywhere. Can you identify this solidification mechanism in any other process? Can you please mention in the chat where you can see similar solidification process in any other processes? Where can you see solidification or freezing? Any of the manufacturing process? Okay. Anyone know what is solidification? You can simply put in the chat, or you can unmute yourself and speak. Now, anyone know about freezing? At least. Okay. When cast metal in mold solidify. So that's what. What is this solidification? I'm asking. In simple terms, you can say phase transformation. One phase is getting transferred into other. In casting process, either liquid is converting into solid or solid is converting into liquid. This phase transformation that is occurring in between, we can say as a solidification. Liquid to solid transformation, we can call it as a solidification. When you see this in reverse, solid to liquid, we call this a melting. Okay. In this solidification, there are some similar processes. You already know. I'll just write. So similar to this, this certification is common in welding. Is it is also common in 3D printing of metals or additive manufacturing. Okay, in welding, you see this weld pool, right? Which is also having similar, it get, you heat it with any type of sources, gas or arc, anything, you can see a weld pool formation followed by the solidification. And similarly in 3D printing also, even if there are two types, in whether you use powder bed or wire direct energy position, you will get that, weld, that liquid pool in it, and you'll solidify it. So that mechanism is common in all these such process, and which is also common in casting, which is starting of the casting. So if you see casting in a way, you can directly apply in all the process like welding and 3D printing. So that is in simple words, casting is like simply converting, a liquid metal into a required desired shape just by making the use of fluidity of the melt. You can do that by using forming also. Suppose if I want to get a certain shape, I can use, good forming tools or dies. I can get a required shape, but that also I can use. But in casting we are making use of fluidity, you know that's the main basic introduction to casting. Then see some of the advantages as mentioned in the class. We can cast as big as bigger components such as, if you see the casings of any turbines, very big casings, or if you see the propeller of a ship, it will be nearly like 2 bhk flat, that propeller, that big propellers you can easily make with casting. And also even you can make, thin castings as well with different types of process if we will use, but you can make by casting process. And complexity we can, of course you will know, I will not much dwell into it. Then come to this, some of the metals can be casted only by using cast iron, because the toughness is very low for this casting. So for cast iron, so we have to use casting for this type of metals. And it will, there are some certain properties such as this new toughness or lightweight metals, we have to go for this casting process. And this is the most, low cost process, we can say. So the this 3D printing, additive manufacturing, that was like popular in this era, the cost is not satisfied. Even you can get whatever design easiness, but the cost is too much as of now. But the only disadvantage is in
Sir,
casting is labor. Yeah.
sir, is 3D molding, 3D printing is a casting process?
No, no, no. The mechanism in 3D printing is a casting process.
Okay, okay, sir.
Yeah. When you heat whatever the powder or the wire metal, it will convert it into liquid, then solid, right? So the transformation is happening. That
Sir,
solidification
but we
is
use
common.
in 3D, sir, but in 3D printing we use actually plastic or uh, those type of
Yeah.
materials which,
Okay. I think you missed this part, right? Sorry. You missed, I think, this part. Metals. 3D printing of
okay, okay,
metals.
sir, okay, okay, sir.
Then the old disadvantage is the, it's a labor intense process. But nowadays, if you just Google it, or if you see in YouTube, just the manufacturing of Ford engines. So they have put in the YouTube. So if you see Ford engines, so the block is made by this casting process. I think mostly 90% of the process is automatic. From the pattern making to taking out the product, 90% of this process is automatic. Everything is automatic. Pouring the metal into it and taking out, everything is assisted by these systems. Only few operations are still done by the labor. Okay. That is being over, this disadvantage is also being overcome in coming future. So with that, I'll just briefly explain this casting step. These are also explained in the class. I'll just briefly explain. So we start with the pattern making. We also need a core if you want to produce any hollow components. Then we'll go for the molding. Molding is nothing but making this cavity using this pattern or core. Then we'll just melt the metal and we'll just pour it in. We can do this in mass production also. It is not only about one part. We can do this in multiple parts. So, 3D printing is also, a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D printing is also a very simple process. It is not only about one part. We can do this in multiple parts. So, 3D p Yeah. So if you see, I have mentioned to let me give a question. Then I will start this verification. Then it will be a little more interesting. I'll just draw two types of microstructures, and just tell me which microstructure represents which process and which I will write the bottom also. Which one is this? So right now I'm just seeing this. Sorry, uh, pure metals. The second one is alloys. Means there are some alloying elements in it. So these are one and two. I will just draw two random microstructures. So this hashing represent the sand. If I'm talking about the sand casting, there is you can draw the heat from this the solid that that border. So now okay, I will explain this whatever I have drawn. So basically, so this is the wall. All the three sides I can take a wall, and the top is open to atmosphere. And I have this is the skin that was formed. This was the skin here and here, and these are the columnar dendrites, and these are again equiax dendrites. So now tell me, which one is a metal and which one is alloy? Okay, let me give A and B. So which one is pure metal in these two microstructures? If you have any doubt, just ask me. I will explain again. I will ask the question again. Pure metal is A, correct? Anyone else?
A is a pure metal.
Yes, yes. Let others answer. Okay. Yeah. Whoever answered that is one correct. A is the pure metal. Since you are seeing this central line
Can I
here.
ask you one question?
Yeah, sure.
Uh, how can I this video is recording? Is this possible for recording?
Yes, sir. The recordings will be available.
Where the option? I can't see.
No, no. This I am recording right now.
You okay?
And these recordings will be available to you via link in the same website.
Okay, okay,
Yeah.
okay. Thank
There is no need to record from your side, your end.
you. Okay, okay.
Yeah. So coming back, and this is 2 hours lecture. Just remind me. I will give one more link at 7 o'clock. If this link is not connecting, you can directly connect to that link. Otherwise, we can continue 2 hours in this link because there is some limitation for Google Meet for 1 hour, something like that. If it is not so, we'll continue. Otherwise, I will provide a link in this chat. Okay, coming back. So I asked this question just to realize so in metals we will I will explain. So the answer is correct. The first microstructure is for pure metal and the second one is for alloys. So in alloys at the center you will not get the central line. Instead you will get equiaxed, this grains you can say, followed by the columnar, followed by the equiax. So the reason I will explain. So in order to know that reason, we should go back to this cooling curves. Okay, and we need to understand how a cooling curve appears in case of metals as well as in case of alloys, pure metals and alloys. So this cooling curve is nothing but a line graph that is representing the change of matter. It can be anything, but in this case, in casting process, we use mainly from liquid to solid transformations. So if you see on x-axis we have time, on y-axis we have temperature. So we are starting from we'll always see the cooling process. We'll never go in the reverse way. The same things happen in reverse way, but we come from higher temperature to lower temperature for easiness. So now so this is the pouring temperature. From that point we are cooling down. So this is the superheat that you need to give in order to heat it, or super cooling is undercooling is what, in order to transform it from the this liquid state to solid state. In pouring, this is the superheat that we provide. In casting process we need to provide the superheat because we from the crucible, suppose from the furnace to the molding zone, if you say, we have to carry it. So there is some time that is being given. So this superheat we will heat more than its melting point, so that while pouring we'll have some time for the pouring the metal. So that is the superheat that we are giving. So followed by pure metals we will have a constant temperature line while it is transforming from solid to liquid to solid. So that is also called as a thermal arrest. In this time, what happens is the latent heat of this liquid is being rejected, and it's slowly converting into solid phase. So this process, whatever happens in this, is nothing but this solidification process. Okay, followed by the so this, after once it is done, we'll get this solid product out. This is what happens in pure metals. But if you come to this, this alloys, this curve is not a straight line no more. It is an inclined line because of the combination of different types of alloys or different types of elements, I can say. Simply if you can see this, some of the examples. If you want, I can give copper nickel is one best example, and zinc tin. If you go and see these type of figures for particular composition, so these cooling curves will be for one particular composition. And in order to construct this phase diagram, we need all such compositions combined, then only you will get these phase diagrams. So in this we will have a range of during this solidification we'll get a range. Instead of a single temperature, you will get two different temperature from where the liquid started and the solid completely transferred to solid. So we call this as mushy zone in general. Okay, in for this particular composition. Okay, I cannot exactly call it mushy zone. I can call it in case of phase diagrams, but for example I have just shown. In this state we'll have a both liquid and solid coexisting. So that is of the this is the one reason you see this cool. Just remember this in your mind. We will have a range for alloys, whereas in cooling curves we'll have a certain temperature, certain only one temperature. So now there is one more aspect we need to understand in order to
So what
understand this
happens in the
certification
mushy
methods.
zone?
Sorry.
So what happens in the mushy zone?
Yeah. I will explain. So before that, we need to understand this free energy. So finally, I will get into that. What happens in this machine? So now, this free energy curves. So it is very simple. Instead of free energy, this is common in everywhere. Anything that is it is at a state means it was searching for a stability. A simple example I can take. So in daily, we see this in any components that are made of this iron, which was actually an iron ore. which is nothing but an oxidized state of iron. So that we purify into iron, we make into nice shiny metals. Okay, and if you keep this in atmosphere, since it is not stable, its stable state is that iron ore only, the oxidized state only. So what happens, it start oxidizing and it will again go back to its original state. Why it goes to the original state is, it is not stable at that, it is not stable in the process that we make. This duration may take years and years. It can take more number of years in which our function is satisfied, but it will go to a stable state every time. That was the scenario that happens in nature. Similarly, here also there is one a term called free energy. So we are talking about this liquid to solid transformation all the time. Why this liquid is needs to transfer to solid if I decrease the temperature? Because it has a free energy to transform. It should have a low free energy. So if I say this is liquid, see this is the melting temperature. If we go above melting temperature, the free energy for liquid is less. So that's why it completely transforms to liquid. When I come back, the free energy for the liquid is higher. So that's why it again go back to the solid form. So if I go back this side, it go back to solid form. If I go this side, it again goes to liquid because of the free energy. It was stable in that state. So that is what the one free energy. So you need to keep in mind this free energy as well as this freezing range. Now now I will explain. So there was a question earlier, why what happens in machining. So keeping in mind these two things, so there was two types of nucleations actually happen. uh, I'll just explain briefly, then I will go into deep. So uh, this heterogeneous part is nothing but we need some, so generally we call this inoculants. Inoculants are grain refinement particles, are foreign particles. So these particles, when they are present in the liquid metal, these will serve as a substrate for the formation of nucleation. So that's why the formation of nucleation in heterogeneous, the rate of nucleation heterogeneous is very high. But in homogeneous, no such thing exists. It was, the probability of formation of these particles everywhere is uniform. So that is what homogeneous nucleation happens. But in general, we never prefer homogeneous nucleation. We always go for heterogeneous nucleation for its better microstructural properties. Now, in homogeneous nucleation, suppose this is a tank. Just assume which was in sand. You can take sand or any metal mold. I just poured in a hot liquid inside. So when I poured initially what I assume is this complete lad, this whatever mold, I can say this has cavity. In the cavity is completely filled. So the cavity is till here it was filled. Okay. So what happens? Whichever the liquid that is in contact to these surfaces, it will solidify instantly due to this chilling effect, and it forms very small equiax grains. Okay. Now what happens is that so this is the q out. Q, I am writing Q for heat. So heat is getting rejected these directions. Okay. Now what happens if you see in this phase, in this cooling curves? So this during solidification process, we are getting latent heat release. This latent heat release by this, this small aqueous grains into this, it will release this latent heat in the all the directions. So one direction maybe this side, one direction maybe this side, top, bottom, everywhere. So generally what is happening is, due to release of this latent heat, the temperature inside this cavity is getting increased because of the release of this latent heat. So the latent is getting increased. So again, it go backs. So as I explained in the free energy curves, if the temperature increases, it again go back to liquid state instead of forming these solid crystals. So that is what happens is, the new grains cannot nucleate easily. This I can explain very neatly in in a nice derivation form simply. So we have two types of, generally we have two types of energies. One is the surface energy of the nucleus that is being formed, or the other one is the volume of the same nucleus. When it forms, we generally assumes it is a sphere. Initially, it actually forms in a small, nice, very small sphere. Then, while evolving, there will be so many disturbances for this embryo while evolving, so that it will transform its shapes to some different types of shapes. For example, a dendritic structure or a faceted structure, a different structures. So this surface energy is nothing but, for simplicity, we assume it as a sphere. So surface energy is nothing 4 pi r square into gamma. Gamma is nothing but the surface tension was present. Volume is nothing but 4 by 3 per year pi r cube into this delta z. Delta z is nothing but the Gibbs free energy available in that. Now if I see the total energy to the summation of these two, so whatever this temperature I am talking, this temperature is nothing, is a this delta z is nothing but a function of this temperature. I will write the complete form for this delta z so you can make out. So this is the energy of a nucleus that was formed here. But this nucleus will not evolve, or it will evolve, or it cannot evolve. There are two probabilities. So there is a certain radius for it, above which it can develop, or below it cannot develop. So that why I am saying it cannot develop, that also we can see just from this derivation. Just a second. Yeah. So in simple terms, so this surface energy is nothing. Yeah. So this surface energy is nothing but this uh, surface area. So this depend on the surface area of this sphere divided by the volume. If you, for a sphere, if you write this, you will end up getting 3 by r. So this r is in the denominator. So suppose for a small sphere, that means if r tends to 0, this energy for surface energy is too high. It is almost infinity. This surface energy, I will write delta fs. The surface energy is infinity if r tends to, if r is tends to 0, means if the formation of the new nucleus is very very small, the surface energy is too high, so it will finally come, it cannot evolve, because the energy of the surface energy is nothing but maintaining its shape, you know so it cannot further grow, rather than it will dissolve in the liquid itself. So for the formation of this new nucleus, this r should marginally should be higher. so that the surface energy that is bonding the sphere will be less, so it will start evolving slowly. So we should get this optimum size of this nucleus just by if you see, whether I will take new note. Yeah. Yeah. This is the total energy delta Fs. So we have two components I mentioned. One is the surface. The one is the volumetric energy. Nothing but that gives energy. So this surface energy is always positive. So when increase in the radius, it will always increase. Okay. For a temperature T naught. But this delta Z, it is always negative. While this transformation can happens, only this free energy is negative. So this delta Z is always negative. Only if it is negative, this transformation will happen. So that's why what happens is initially this will decrease. This is nothing but this volumetric factor. This is surface. So the resultant of these two, delta F is nothing but summation of these two energies. So initially it will increase, then it will reach a critical value, then it will fall down. So this is the critical value, and this is the critical energy barrier for a nucleus. It has to overcome this energy barrier in order to form a nucleus. So whatever these small nucleus forms before this, we call it as embryos, and whatever it forms after, we call them as nucleus. Okay, this is the R star, or the critical radius for a nucleation. We can easily find this R star just by differentiating this delta F term, because we have a constant slope, so the derivation at that point is zero. If you do this, you will end up getting this R star value. Do anyone remember what is this R star? No. Okay. So this R star value is nothing but this. 2 comma divided by delta z. Actually, if you do this derivation, you will get minus 2 comma divided by delta z. But since delta z is always negative, I am just writing it positive so that you can keep delta z always positive inside. Generally, the values will be negative, but you can keep in positive so that our formula will be correct, because r is a radius, so it should be a positive quantity. Uh, so you should not get a negative. That's why I'm just writing delta z. Actually, it is a negative value, but you have to keep positive value inside for getting this critical radius of thickness. So the critical nucleus radius. So this is the minimum radius that you need to get in order to form a nucleus. So now this delta z is nothing but this is the formula for this delta z. This we also can write as delta d divided by delta m. Okay, and if you keep this delta z value in r star, you will get very nice. Instead, I can keep directly in delta f. Then it that energy barrier that I'm talking. So we can deduce some conclusions from this derivation itself. And you need to remember this formula for solving some of the numericals as well. So now see, just forget about every derivation that I've just discussed. Just concentrate on this final formula. So if you see there is delta h term in the denominator and delta t term in the again delta t in the denominator. So what happens if my delta t term is 0? Anyone?
The result will be infinity.
Yes. So that barrier what that I'm talking about will be at infinity, so that it will never form. The nucleus can never sustain. It will dissolve in the liquid itself. Similarly, this delta H term, if you see, if it tends to zero, that whatever fusion heat, that enthalpy of fusion, if it tends to zero, the similar thing happens. So that is the and we have several other factors also, but you need to concentrate on the only these two factors for now, because this was the barrier that was I'm discussing in order to establish this nucleus in the liquid metal. Okay. So now, so having understood this concept, then we can go back into the nucleation of fluid metals. Okay, that is how they represented this formula.
Yes, I understand now.
Yeah. So now this K and C, this C is mainly depend on the superheat you put. Superheat is nothing but the temperature. Suppose if I say 600 is the melting temperature, but while pouring, if I keep 600, it will so someone said homogeneous nucleation. Everyone is agreeing with it. Is it homogeneous? Uh, if just one small announcement, if by chance if there is any connection problem you are getting, just relog into the same meeting again. Okay. I think it is already 1 hour, but there is no disturbances such that. Okay, let go back to the question. So, what type of nucleation it is? Someone is saying homogeneous. Anyone with the heterogeneous? Okay. So I think so. In this homogeneous nucleation happens, and there is a equal probability for formation of this nucleations, whatever. But in heterogeneous, we will have a foreign particles. It can be anything, na? It can be surface also. Even the surface of the mold is acting as a aid for the nucleation. You know, and the probability of formation here on the surface and inside the liquid is different. So it can be, it is a heterogeneous nucleation. Understood? Or shall I explain more? Okay, let me just quickly explain. So the inoculants are any particles. What exactly they are doing? So if you take a small liquid, suppose this is a box, there is a liquid inside. I have a particle here. So now if there is any nucleus has to form, this is there is a surface already available. So I can just start here and I can evolve. So what happens in this case? I need very less energy to form this embryo because I don't have to completely form a complete sphere. Instead, I can just form a half sphere itself, right? So the formation of this new nucleus is easier in my case. This is
And
particle and this is the nucleus. Yeah.
when I use the inoculants, then the grain structure is a very fine. That's why
Yes.
we are used in inoculants.
Yes, sir. Yes. Yes. True. So, but in the similar case, if I have a surface here, so if there is a grain formation here, so it is easier, right? uh,
Yeah,
the formation easier. So on the surface also it is forming easier. So what it does, it means it is also a heterogeneous nucleation. It's not a
yeah.
homogeneous
You
nucleation,
are right.
right? Yeah.
Yeah,
So that so now coming back, so this initial thing is heterogeneous. So you don't need any particle to form a nucleus, then you can call it a heterogeneous. Anything that is supporting for the formation, you can name it as a heterogeneous. Homogeneous, there is nothing aiding in it. It has to form within it is itself due to some concentration or thermal gradients. So now so once this is formed, it will release some heat into the liquid region. And so due to that, what happens is, so the time or the temperature, and we have a barrier here also. This here it can easily heat can get extracted, but here it is releasing latent heat. So now the time required for cooling it is even more, because now it is at higher temperature compared to this the surroundings. So instead of forming this what is this and this is a chain reaction kind of. So once it is formed, if there is any nucleation happening here, it will also release latent heat. Slowly what happens is, generally in pure metals we can see a columnar structure here with the center line in middle. Similarly with the bottom also. So this is only the half part I have drawn. Similar thing happens in the other half also. So this is microstructure that happens in pure metals. But as I asked in earlier question, so in this alloys we got a different after some time we got again these fine structures, right? So now we have to find why it is forming. And this growth is we call as preferential growth. And growth is in and remember one thing, so heat is getting lost in this direction, but our growth is in direction. So in every case the growth is in opposite to the heat flow, yeah, heat extracted surface. So now and these are equiaxed, and these are columnar grains, columnar grains. And these are the equiax structures. These are fine equiax structures, I should say. So now let me see the same scenario in alloys by after some time. So this is the scenario that happens because of latent heat release. So and the slow cooling range, we will get a very nice columnar structure. But so this is in case of pure metals. But in alloys we will get a after some time again we will get this equiax structures. So now let us see why it's so. So now we have to remember all the concept that we have discussed earlier. The first concept is this phase diagram. So let me take one small binary alloy. Okay. So now, if I, for any temperature, say this is one temperature. This is say some point A. This is TA. Sorry, not TA. This is CA, the concentration at A point A. And this is the solid. This is the liquidus line. I hope you know this is the solidus line. This is liquid plus solid. So in this liquid plus solid region, if you come left, this is the concentration in solid, CS. This is the concentration that we have in solid. Whereas right side we have concentration in liquid. So if you see, the concentration in solid is becoming lesser. Actually, this is the concentration it should have, Ca actually, but it is when it is coming completely into solid state, this solute whatever, this is solute, we have to say percentage weight of solute. Suppose if I take any uh, aluminum copper, this copper is a solute in this. So this copper or any solute will be getting rejected into our liquid, the region which is in liquid state, and the solid is having very low this solute content. Okay. Now if I draw a diagram, if I want to see this in a very nice form, so what I do, so this is the CS, nothing but the concentration in solid. This is at point A. So what happens immediately? This is the actual content, uh, percentage C. But before it will be less, but after it will is more, and we will have a spike and a this region I'm telling, we have a spike followed by a drop in the concentration. So this spike we are getting because of this rejection of this heat during this solidification process. Now this happens at so many, this happens in different times of freezing rates or heat extraction rate. If my heat extraction is more, there is no time for this this heat rejection. If it is, the heat rejection is less, there is good time of for this solute to reject into the liquid. So this region, it depends mainly on this cooling rate, to be precise. So now if I want to, if I see this in terms of that cooling rate, so this is the solid that already formed, and I have this spike coming up. So now if I this is the actual cooling rate that I should follow, that is one which happens exactly in pure metals. But instead, if at all it generally it happens in this range for alloys. So there is a region, this is undercooled region. Okay. And similarly, if my this heat extraction is even less, I will have even more undercooled region. So this undercooled region is the main factor of formation of these equiaxed structures in alloys. Okay. Any doubts? And this columnar structures also will not be columnar, it will be dendritic because of this solute rejection or inhomogeneous distribution. And this is in dendrites in general, these composites, these alloys. So if there is any, so say this is the dendritic structure. Dendritic structure is nothing but a root structure of a tree. If you see the roots of a tree, or if you see any coriander that leaves, you can see that structure, right? That big branch root is coming, then followed by the small branches. So this is like a dendritic structure. Similar thing we'll see in metals. This is very simple dendrite that I have drawn here. It can be any symmetric, even it can so there will be main thing followed by the substructures. Even in substructure they will form again, and even in that it will form again. So there is repetitive kind of. So it's this is the dendritic structure. While evolving these dendritic structures, so basically these will evolve in all the directions. So finally what happens is at a certain points, at certain time, so these will collide, they will touch each other, and at the center there is no liquid at all, and there is a void, there is a shrinkage happening in that. So that's why we'll get this shrinkage. These are very small minute shrinkages that we get. We can get gas shrinkage and solidification shrinkage. This we call as this solidification shrinkage that happens in these alloys. Okay. And this can and this solute, and in this region we will get a very rich solute region because of the rejection of this solute into this small undercooled region. Okay. This is the concept uh, that was mainly discussed in this entire first week lecture, just to understand what is the solidification mechanism that is happening, and what is the critical radius of nucleus, what is how does a microstructure looks in alloys and in pure metals, and why is it so. Okay. So this comes to the last topic. I will finish in a while, then we can go for the numericals. This solidification time. This is very straightforward formula, I can say. And there are some. There is one more concept. You can just read it out. It is very interesting. Freeze wave, which is very interesting way, because we can easily say whether I can whether if I give a superheat temperature for you, whether is it easier for me to cast it, or whether it is difficult for me to cast. So that freezing range you can easily get just by studying these freeze waves for any particular alloy or particular metal component system. So let me. There is one more thing: central lines feeding resistance, which is also related to this same freeze wave. Okay, this is in short. I will just explain in short. Similar thing happens. So if you this is the central line only in pure metals. So if I take a point, if I take a line here, and I take 1 point here, 1 point here, 2, 3, 4, and if I see the solidification times, can you tell me which is going to solidify at the end? So I have drawn 1, 2, 3, 4, 4 points. Which will be
The
solidified
point
at the
at
end?
4. The point at 4.
Yes. Yeah. So if you see this ranges, this is the mold phase, assuming this mold, and this is the central line. And if you see, this is the start of solidification, and this is the end of the solidification. So this is the starting, and this is time. End of solidification. So this is the mold surface, Initially it was here, and finally it was here. So this is the solidification time for the grains that are near the mold surface, and this is the solidification time for the uh, I have to add this part also. This is the solidification time for the grains that are at the exactly at the center line. If I draw this line, so by the time the grains are solidified at the surface, still there are some parts which are not solidified near the center line. So this type of freeze waves, we can study, and this is the width that explains whether it can solidify faster or slower. Suppose if I want to see similar, this is for a sand casting. Suppose if I take a die casting in which I will use the mold surfaces as a metal, it will be like this. It will be like this because instantly it will solidify, and this range is also very less in my case, in die casting case, whereas in sand casting it is wider. So that is what this center line feeding resistance determine indicates. This is the solidification time at the line divided by the total solidification time. Okay, that was the simple concept. Then we'll end start discuss this solidification time. So this solidification time is, there were several formulas for the solidification time also, but one simple formula is this Chernivos rule. That is, solidification time is nothing but volume by area whole square. That is nothing but solidification is some constant V by A whole square. And remember, this constant is a dimensional constant. Can you anyone tell me what are the units of this constant C?
second per meter square.
Yeah, right. Nice. So that was so. Don't believe all the dimension. This constant will not be a dimensionless constants. Some constants will have dimensions like this case. It has a seconds per meter square. So whatever you keep in this formula, you should maintain those. Suppose if someone is given this solidification time in minutes, and this c value in second per square and v value in meter square, you should convert this. Don't go blindly with the form values given in the question. We should convert this because it has a units in this. Don't take direct value. So there was a small mistake that people often do this. So this was the solidification time. And if you see a little bit more, this c value, it depends on several things. One is this sand properties, sand properties, mold material that I'm using, and pouring temperature as well. And these two, this is actually, this exponent can be any value. 2 is for metals. Okay, that is the the topics that was covered in this entire week, this week one especially. And if you see this this formula is very interesting. Even without this also you can make out. So in general, volume and surface. So actually volume represent heat content in any component. If the volume is bigger, so it can store more heat in itself. But surface represent heat transfer in general. If I have a large surface area, it is more useful for transforming the heat. For example, in fins, in heat transfer, fins we will use because it has a very large surface area. So it will have more convection heat transfer. So uh, these are the two factors. So if I have we should take this ratio in order to determine this solidification time actually. So there is a very big, say I have a very big block. Suppose V by A ratio, I have some value A, and I have very small block, and this b by a value I have b. Okay, if I want to see which one cools faster, in that case, uh, just tell me, in this case I have a greater than b. So what exactly, object 1, object 2. So in my case, I already calculated v by a values for a, component 1 and component 2, and I got a greater than b. So what it represents? Which one cools faster, a 1 or 2?
2.
Okay. Yeah. Someone raised hand. You can speak out. Okay. Why 2? The answer is correct, but why? V by a ratio is more or less? Okay. Yeah. Perhaps I should have kept the volume constant in both the cases. Just let me modify a bit. It will be easier. So in my case, the both the volumes are same, but I have an extended surface in this, so that my area is more. But I kept the volume. I have taken care of the volume so that both the volumes are same. Now tell me why B is cools faster.
So because B has a surface contact with some area where heat is mutually transferred.
Yeah, true. Then I can why I need a V by a value. I can just take A, right, in my solidification time. I'll just quickly explain. See this V by A value. See this A is always in denominator. This we also call this as a modulus. If I have a more surface area, so that means my entire value of this modulus is becoming less, right? With respect to volume, I'm taking care of volume also. So that's why we need we should need both V by A, V and volume both instead of only A in this case. In case of calculating this time for solidification time, it is nothing but mostly heat transfer problem only. Simply, suppose if I have a quantity A, quantity B. Suppose I have two quantities, Q1 and Q2. Q1, say some 100 kilowatt energy I have, 100 kilowatt, and then 20 kilowatt. Suppose if I want to calculate how much time one surface a block takes from 100 kilowatt to 20 kilowatt, I can just take this surface area. I should take the values of both volume and area in order to calculate these things. Okay, that is what entail I want to convey from this simple certification time experiment. Instead of just remembering this formula, so this was the backend that was actually there in this formula. So always remember this is B by A. A should be the denominator, so that it is reducing the time. If you increase the surface area, it will reduce the this modulus value, so that the time for your solidification will reduce. I hope I made some small points. So let us now start some numericals, starting with this. Just spend 1 or 2 minutes, then we can discuss the answer. If you get the answer, just put it in the chat box. Anyone with the answer? Say this is A, B, C, D. You can follow. Someone with C. Okay. This is that R star that I actually derived in the session. So generally, if I remember, this Gibbs free energy is in the denominator, and there is a two value on the top with a surface free energy. Is anything matching here? How B? Okay. How B? How C? Okay, let me go back to this small derivation. So this was the derivation, right? C. No, answer is A. 2 comma divided by delta ZV. Clear? The right answer is A. Okay. Then let me see the second one. Just solve it. The second. Next question. Yeah. Okay, we have answer C. La- so large undercooling near the mold walls leads to the formation of dash near walls.
Answer is B.
B. Columnar grains. Okay. Anyone? Someone also with A. I think one gets the correct answer. That is small equest grains. See, this is the mold surface, right? Here we'll have very large undercooling. Why? Suppose my mold surface is say some 200 degrees Celsius. I am pouring the metal with 600 degrees Celsius for aluminium. So what is the difference here? 400, right? But when you go slowly inside, it will be always less than 400 because inside the temperature will be more than 200. Understood? So that's why we'll always get small equaxed grains, not the larger one. You want to get uh, yeah. If you want to get larger grains, I should have a a constant reduction. Okay. Any doubt in this question? Next question then. Just take some time and spend. Just we'll see. Just a second. Just solve this question. I'll just come.
One, two, and three. ABC. Means third answer. One, two, and three sentence is okay. Fourth one is for homogeneous.
Yeah. Yeah. Sorry. Can you repeat once?
First three for heterogeneous and fourth one is for homogeneous.
So your answer is C,
Yes.
right? Okay. Okay. Okay, let us see. So this is they are asking for heterogeneous nucleation. Foreign particles assist in the nucleation. So one is correct. So I can remove this D option here. Foreign particles alter the solid liquid energy. Okay. Then two is also correct. Then I can remove A. Degree of supercooling requirement is less compared to homogeneous nucleation, which is true. So option C is the correct one. And fourth one, probability of nucleus at all the side domain is same. So this is true for, as someone already pointed out, for homogeneous nucleation. Okay, I think this is straightforward. Let us see.
Answer is C.
Okay.
The answer is C.
Yeah. Thanks. Next question.
Can you please explain the numerical?
Yeah. Sure. Just wait for 1 or 2 minutes. Let us see if anyone answers. There, I'll explain. Yeah, if anyone is trying, please try. So we have spherical drop. radius 2 mm, solidify in 10 seconds. Similar drop of radius 4 mm with solidify in dash. So generally what they want to means this whatever. So if I write the formula T is equal, T solidification is equal to C into V by A whole square. They indirectly saying that C is constant in the both the cases. Okay. So generally, if you have seen this V by A ratio is D by 6 for sphere, cylinder of height with the same height as diameter, as well as cube of side D. For all this, if you see V by A ratio, it is always D by 6. Okay, so that gives us Ts is equal to C into V by A whole square. That implies C is equal to V by A whole square. That is T solidification V by A is nothing but D by 6. Here, okay, I can directly write D by 6 whole square. That is D 36 Ts by D square. That is 36 into Ts is given as 10 seconds and radius is given 2 mm. So diameter is 4 into 10 power minus 3 meters. 4 into 10 power minus 3 whole square. It gives the value of C, and they are asking a similar drop of radius forever would solidify in. So this is also radius. TS2 is nothing but whatever the value you will get, that is 360 divided by 4 into 10 power minus 3 whole square into this diameter will be here 8 into 10 power minus 3 by 6 whole square. Anyone? Anyone with the answer? Let me calculate.
20 seconds.
Okay.
Fourteen, 1 4 second.
Okay.
Answer A.
Someone is 14. Okay. Let us see. This is the thing you have to calculate. Okay, someone. Anyone with 40? Sorry. Please check. You will get 40. Shall I move to next question?
Yes.
Okay. So this was the question, related to the. This was derived in the class. And you can derive, you can do here also with this. So they're asking the ratio of surface energy to the volume energy determining critical radius during solidification process. So if you know this critical is nothing but generally I neglected minus, but there will be minus. Okay, this is the critical radius formula. Then what is the surface energy? Surface energy array delta of this 4 pi r square gamma. Volume energy is delta z. Okay, you just have to substitute this r value here as well as here and take the ratio. Can anyone do that for me quickly? Okay, already calculated. Here A is the correct answer. Okay, can we move to next one? Okay. If any doubt you're having, we can ask or we can move. Anyone with the answer?
Answer is C.
Okay. So these are the formula. If I want to write in terms of, so T4 is nothing but time end for center line minus time starting for center line divided by time end for center line minus time starting for the surface. Okay, it will be answer A.
Okay, sir.
Yeah. Okay. So these are the some of the questions. If you there was some questions which were derived in the class itself. If you have any doubts, you can stay. These are the questions that I will be solving in next few minutes. These are already solved in the class. If you have any doubts in these questions, you can ask.
Excuse me, sir.
Yeah.
Hello.
Yes.
Sir,
Yes.
in final exam also such problems will ask.
Yes. Problems
Uh,
will come from numerical. This
uh,
formula based.
Almost all question are like problem solving or descriptive
I
MCQ
think they
type.
are there are combined actually. You'll get
Okay, combined mode. Yeah.
yes. Yes.
Okay. Okay. Thank you, sir.
Yes.
And this is the all MCQ type.
No, no,
Is it
I'm
all
not
MCQ
quite
or
sure.
MSQ?
I'm not quite sure about, but they can do whatever they want. They can do MCQ as well as fill in the blank type questions.
And MSQ for 2 numbers.
Yes, yes, just like that. One question we ask, right? Mostly this will be this type of questions. Otherwise, they can give fill in the blanks also, but I'm not quite sure about it.
And I want to know the this is the doubt class is the ending the or the continue for 2 weeks to 3 weeks.
Nah, it will continue. It will continue till the end of the course every week.
And you will describe the SGRN part.
Which part?
SGRN is the ductile iron part.
Okay. Uh, I did not explain in this session, right? Are you asking about this or is something else?
No,
No, it's
this no.
cast iron.
Is a cast iron. I will asking
Okay,
some SGRN or steel casting. Is the
okay,
call
okay,
is the ductile iron and steel casting.
Okay, sir. Actually, this session I was, I prepared according to the week one session. Actually, there will be
Okay,
8 weeks. So in the next
okay,
week, there will be week two session.
okay. And if you don't mind, can I ask you, are you a student or
Uh, yes, sir. I am a doctoral student at IIT Bombay.
IIT Bombay?
Yes, yes.
And metallurgy is your stream, I think.
I am from manufacturing stream, from mechanical engineering.
Okay, manufacturing stream.
Yes, yes.
Yeah, thank you.
Yeah, thanks, sir. So there was a question: what is the solidification curve for brass and inside sand core or mod? Is same core of alloy metal? Yes, it will be same for alloy metal since it's a binary alloy. I think brass is a binary alloy, right? Okay, let me. Yeah, if you have any questions, you can stay. Otherwise, you are free to carry on with your own work. Thanks for attending. We'll meet in the next session.
Okay, and please upload the recording classes.
Yeah, sure, sir. Sure.
Okay, thank you for
Yeah.
your class.
Yeah. Yeah. Thanks. Thanks.
Okay, sir. Thank you very much.
Yeah. Thanks. Thanks for attending.
Thank you, sir. Thank you.
I'm not quite sure about this question you are asking, but in general, this is like fundamental way we look. So generally, for alloys, we'll get the structure in the center, whereas for normal pure metal, we'll just take columnar structure and we'll get a center line. So according to that, if I apply for brass, it's I think a copper binary alloy. So you should get the alloy structure ideally. Uh, So I am seeing this phase diagram for this whoever asked this question. There is a if you can go to phase diagram of this brass. So there are so many phases in this. So it actually depends on what concentrate percentage of zinc you are taking, and we have so many phases such as alpha, beta, gamma, delta, and so accordingly you have to select the things. So because we have different phases, so the behavior may not be the so whatever I explained is for very ideal case. Okay, 60 to 40%. In that case, you have several phases, 62%, 60 to 40. So you have alpha, beta, and beta prime also. So I don't know what is the microstructure they form. Based on these phases also will influence this shape. So I think we can, if there are any literatures, you can search based on the microstructure. Accordingly, you can make out. So there are so many things that actually influence the shape. So we are just mainly concentrating on the temperature gradient, but there is also solute gradient actually composition gradients. So these two factor actually plays important role to discuss it. Yeah. Thank you for. If there are any questions, you can ask. Otherwise, we can end the session. Yeah. Okay. Okay. Yeah, no issues. Okay. So yeah, thanks. Mitesh, if you have any doubts, you can ask. Otherwise, we can end the session. Okay. Yeah. Thanks. Thanks for attending. See you in the next class.